Explain the influence of load position on SF and BM variations. In beam analysis, where a load is placed matters just as much as how big the load is. The position of load directly controls the magnitude and shape of the shear force and bending moment diagrams. Influence of load position on shear force. The shear force at any section of a beam of any section of a beam depends on the magnitude and position of loads acting on the beam. Changing the position of a load alters the reactions at the supports, which in turn changes the shear force distribution along the beam. First one, point load. A point load causes a sudden change in the shear force diagram equal to the load magnitude. When the position of the point load changes, the location of a jump in the shear force diagram shifts, and support reaction change, modifying shear force values throughout the beam. Maximum shear force occurs when the load is placed closer to a support. Uniformly distributed load. A UDL produces a linear variation of shear force along the beam. Changing the position or length of UDL shift the region of linear variation, alters the peak positive and negative forces. The slope of the SF diagram remains constant, but its start and end points change. Moving load effect. As a load moves along the beam, shear force at a given section varies continuously. Influence line diagrams are used to study variation. Definition and importance of shear force. Shear force at a section of beam is defined as the algebraic sum of all vertical forces acting on one side of a section of the beam. It represents the internal force that resists sliding between adjacent sections of a beam. Units are typically newtons or kilonewtons. In simpler terms, imagine slicing the beam at a point. Shear force is a force that tries to slide one part of the beam past the other. The importance of shear force. First one, structural safety. High shear force can cause shear failure, beam breaking, beam cracking along a horizontal plane. It is critical in short, deep beams where shear dominates over bending. Design of beams helps to determine cross section and reinforcement in concrete or steel beams, ensures the beam can carry loads safely without failing in shear. Predicting load effects. The shear force diagrams indicate where maximum shear occurs, usually near supports. Essential for placing reinforcement and connections. Relationship with bending moment. A shear force is a derivative of bending moment. V is equals to dm by dx. Knowing shear helps calculate bending moments, which is crucial for beam design. Shear force is the internal vertical force in a beam that resists sliding between sections. It is important for ensuring structural safety, designing beams, locating critical sections, and calculating bending moments. Effects of load position on SF distribution. The shear force at a section depends on the magnitude and location of the load. Changing the load position changes reactions as supports and therefore alters the SF along the beam. First one, point load. A point load produces a sudden jump in the shear force diagram equal to its magnitude. Moving the load along the beam, it shifts the location of this jump, changes support reactions, which modifies shear force values everywhere along the beam. Second one, uniformly distributed load. UDL causes a linear variation of shear force. Shifting the UDL along the beam changes the start and end points of the shear force diagrams, alters the maximum and minimum shear values. The slope of the shear force diagram remains the same, equal to the intensity of the load. The shear force distribution of a beam depends on the load position. Moving loads towards support increases maximum shear, while moving loads toward midspan decrease shear at the section and shift the shear force diagram accordingly. Impact of varying load positions on bending moment values. The bending moment at a section of a beam depends on magnitude of loads, position of loads relative to the section. Changing a load magnitude or position directly affects bending moment distribution. First one, point load. Bending moment at a section is equals to reaction into distance minus load into distance from section. Increasing the load magnitude proportionally increases bending moment at all sections. Maximum bending moment occurs the load for simply supported beams. Moving the load towards the support reduces bending moment because the lever arm decreases. Moving the load towards the midspan increases the maximum bending moment. Maximum bending moment occurs on a midspan for simply supported beams. Uniformly distributed load. Bending moment at a section is equal to integral of load intensity into distance from section. Increasing the load intensity increases bending moment quadratically because bending moment under UDL is equals to M is equals to W L square by 8 for midspan. Shifting the UDL along the beam, it moves the location of maximum bending moment, alters bending moment values along the beam, especially near loaded areas. Moving load. Bending moment varies continuously with load position. Maximum bending moment occurs when the load is positioned such that it produces the largest lever arm above the section, and influence the lines are used to determine maximum bending moment at a given section for moving loads. Varying the magnitude or position of loads affecting bending moment in a beam, larger loads increase bending moment. The loads near midspan produce higher bending moment, and moments loads shift the location and magnitude of maximum bending moment along the beam. Practical implications in structural design and safety. Importance in structural design. A. Beam sizing and cross section. Shear force and bending moment determine the size and shape of a beam. Maximum shear governs web thickness or reinforcement in reinforced concrete or steel beams. Maximum bending moment governs flange width and depth or main reinforcement. Ensures beam can safely carry loads without failure. Placement reinforcements. A reinforcement in concrete beam is placed where stresses are highest. Bending moment controls longitudinal reinforcement. Tension reinforcement at bottom for simply supported beams. Support and connection design. High shear near support, strong connections required to transfer forces safely to columns or walls. High bending moment near midspan, adequate bending capacity needed. Safety considerations like avoiding Shear failure. Shear failure is sudden and brittle, can cause beam collapse without warning. Shear force diagrams help identify critical sections where shear reinforcement is essential. Avoiding bending failure. Bending failure is more ductile, giving a warning before collapse. The maximum bending moment sections must have enough flexural strength. Load position effects. Loads near supports, higher shear may require stronger connections or stirrups. Understanding SF and BM distributions ensures that beams are strong, safe, and efficient with reinforcements placed where needed to resist shear and bending without over designing. Conclusion. Shear force and bending moment are fundamental internal forces that develop in beams due to applied loads. Their magnitude and distribution are strongly influenced by load type, magnitude, and position. Shear force is highest near supports, governance, shear reinforcement, and connection strength. The bending moment is highest near midspan for simply supported beams and governance, beam depth, and flexural reinforcement. Varying load positions change shear force and bending moment values affecting the location of critical sections and overall safety. Understanding these distributions is essential for structural design, ensuring that beams are safe, efficient, and capable of carrying intense loads without sudden failure. Careful analysis of shear force and bending moment under varying loads is key to safe and economical beam design. Thank you.